This is one of my favorite topics. Drawing Lewis structures is one of the foundational skills for understanding covalent bonding, which leads to understanding geometries, or requires understanding geometries, and leads to a better understanding of intermolecular forces, which ultimately leads to a understanding of the physical properties of substances. So this is very, very important. I'm going to take you through how to draw a Lewis structure, and we're going to begin by having carbon tetrafluoride as our example. By the end of the PowerPoint, we'll be using some different stuff. So here are the rules to draw a Lewis structure. Number one, the most important thing is to add up all the valence electrons from each atom in the compound. And as you see in our example here, with CF4, the carbon, take a look at your periodic table if you don't hit pause and dig it out. But carbon has 4 valence electrons, and there's only one of them, whereas there are 4 fluorines, and they each have 7 because fluorine's a halogen with 7 valence electrons. That adds up to 32. So we need to now distribute 32 electrons throughout this molecule. Step 2 is to divide the electrons by 2, and that puts them in pairs. We're going to assign them as pairs, ultimately. Pairs will either be bonding or non-bonding. That makes sense. 2 makes sense because when we learned orbital notations and such, we always learned that in any orbital, that includes bonding orbitals, there are always going to be 2 electrons, an up and a down, if you will. Step 3, we need to decide which atom in the formula is going to be in the middle. We call that the central atom. So that's a new term for you. The central atom is the one in the middle. The central atom is always going to be the least electronegative of the group. It's not always a pair. It could be 3 or 4 elements. So it's always the least, and that says that in the white box at the bottom. The other atoms become terminal. Terminal meaning ending or outside in this case. So these are the outermost atoms. We call those terminal. In the example here, you can see I've aligned the terminal atoms around the carbon. It doesn't matter how you do it. It doesn't have to be symmetrical. It doesn't have to have any shape. But most people are going to want to feel comfortable adding them with just a little symmetry to it. Step 4, now we need to connect these terminal atoms, and what we're doing here, or what we mean by connecting, is that there's a bond happening. And each bond is going to represent a shared pair of electrons. So I've connected each fluorine to the central atom with a solid line, and that's going to represent 4 shared pairs. So out of my 16 pairs that we had, I am now going to subtract the 4 that I've assigned, and that's going to leave me 12 pairs that are basically just unassigned right now. Those are going to become my lone pairs. Now, in step 5, we've taken those remaining pairs, those 12 lone pairs, and I've assigned them around the terminal atoms. And that's the way you do it first. You start with the outside. You fill up the terminal atoms first. So I went, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And when I did that, I subtracted and got 0 remaining pairs. So I have assigned every electron that was available from these 5 atoms into the bonding areas, and now I have nothing left. I am done adding dots and pairs. Now I have one important note. This is new. Was new for me. Other teachers have been teaching this all along. However, the AP exam last year, in 2013-14 school year, decided that the correct answer for Lewis structures would no longer accept the line to represent shared pairs. From now on, they want to see dots and nothing but dots in your final answer. So my message to you is the third bullet right here. Before you're done, when you've assigned all your pairs, before you box in your final answer, go back, erase all the lines for shared pairs, and put those blasted dots. For single bonds, you'll have the 2 dots. If it's a double bond, you can put, it's basically like putting 2 colons. And then for triple bonds, you'll have 3 sets of dots. Now the note at the bottom of the page, this is just my personal opinion. I hate all those dots. I like, and when I learned to do this, I liked having the lines to show me the difference between a shared pair and a non-bonding or lone pair. So when I'm doing this to work, I want to draw my Lewis structures with those lines there. That helps me with geometry. I think it will also help you be able to assign the geometries later. So if you just want to do dots all the time and you're comfortable with it, do it. You're better off. But when you see me draw these Lewis structures for the rest of the year on the board, I'm going to use lines, and then for our final answers, we're going to have to go back and convert to dots. Sorry about that. That's just the way my freakazoid brain works. All right, so let's do a pretty simple example. Ammonia is a common one that you may have to do. So step 1 was to count the valence electrons. So looking at the periodic table, ammonia is in group 5A, so it's going to have 5 valence. Those 3 hydrogen atoms each have 1. So that's a grand total of 8 total valence electrons. Step 2 was to divide by 2 and put these in pairs. So there will be 4 pairs of electrons to assign. Good. Step 3, assign the central atom. What do you think it's going to be? Yep, the nitrogen. It's kind of common sense. This is an exception to the rule, though, because before I said that the central atom will be the least electronegative. In this case, it's not. Nitrogen is actually more, but it's an exception because hydrogen, no matter what, can never be in the middle. And I'll reinforce that in a moment. So I'm going to assign now the hydrogens as terminal atoms. Before I go to step 4, that says shared pairs. We'll connect the terminal atoms. That was 3 out of my 4. So I have 1 left over. Rule 5 said go back now and put those lone pairs on your terminal atoms. Well, these terminal atoms are all hydrogens. Hydrogen can only have 1 pair of electrons around it. So there will be no dots on the outside. When the terminal atoms are full and you still have that 1 left over, there would be the next rule says go and put it on the central atom like that. Subtract that final pair of dots, and now we have 0 pairs left over. We're done. As long as that central atom has a satisfied octet now, let's check it. So that's 1, 2, 3, 4 pairs. That's 8 electrons. That is an octet. It's done. The terminal atoms here in this case are all satisfied. This Lewis structure is done. Let's go back and let's add the stinking dots. So there's the 2 dots, this hydrogen. Here are these 2 dots. And there we go. Everything's a dot. Uniformity. Now, before I leave this, some of you might be kind of freaked out a little bit by these dots on the central atom. That's okay. It correlates. If you remember back to when we did orbital notations, like for nitrogen, we had helium, noble gas notation, helium, and then we had 2s up, down, and then 2px, 2py, and then 2pz, and it was an up. Wow, this is just out of control. Up, up, and up. And that's exactly what we see here. The 2s are here. The 2p y's and z's and x's are each in these shared pairs. So this Lewis structure shows what we would have expected from our orbital notations. All right, so this is step 6. We kind of previewed this in the example with ammonia. If there are any electron pairs left over after step 5, we're going to put them on the central atom. I kind of squeezed nitrogen in before this because this next step could lead to something a little new, which is called an expanded octet. The central atom needs to have an octet, which is 8 electrons around it. But most of the elements of the periodic table can actually expand and go beyond 8 up to 12. So 8 to 12. So here's an example of that real quickly. Krypton is a noble gas, so it has 8 valence. The 6 chlorines have 7 each. So that is, I believe, 50 electrons. .25 pairs. Okay, caught myself before I got too carried away there. Let's remove that work for a second. I realized that there is a missing charge on this one. This is an ion. It's +2, so let's go back and start that over. The krypton has 8. There are 6 times 7 valence for the chlorine, just like before. And that is still 50 electrons. But now it's a +2 charge, which means I have a deficit of electrons. So I really only have 48 electrons. So we divide by 2, and that's 24 pairs of electrons. The central atom this time is really easy. Noble gases have no electronegativity, so they go in the middle. And then we'll assign the chlorines best we can as terminal atoms. 1, 2, 3, 4, 5, and 6. So I have 18 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So that's it. We're done. We check all our octets. The terminal atoms are all full with 1, 2, 3, 4 pairs each. And the central atom has, in this case, 1, 2, 3, 4, 5, and 6 pairs. It's in good shape also. It's an expanded octet this time. That's fine. Krypton is well down the periodic table. It can have an expanded octet, so it's fine. Now to complete this answer, if it's an ion, we put it in brackets because the whole thing has a deficit and a charge of +2. And also, you would going to go back. I'm not going to do it now to save time, but go back, take those lines out, and put dots in like the test writers want. Finally, before you're done with any Lewis structure, you want to make sure the central atom has its complete octet. That is, when you subtract and it's 0, but we count around like we just did, and the central atom is not happy. We have to do something to fix it. So here's an example where we have to fix it. Here's silicon. Silicon has 4 valence. The 2 oxygens, 6 each. So that's 16. Divide it by 2, and there's 8 pairs. Silicon is in the middle. And then we have the oxygens. Connect. So that's 2, leaving me with 6 pairs to add. Around the oxygens then first, there are 3 pairs, and there are 3 more. So that's 6. I'm done. So we want to check and make sure everything has an octet. The oxygen's good. Oh, silicon only has 4 electrons. That's not enough. It's got to have an octet. So what we've got to do now is we've got to go back and we have to reassign these lone pairs as shared pairs. So the structure will actually become double bonds to more accurately represent the covalent bonding in silicon dioxide. So there's the Lewis structure. And we would go back and replace the lines with dots. Now, every year students look at me kind of questioningly like, what are you doing? How can you go back and take dots from the oxygen and put them on the silicon? We're not doing that in reality. Now, we're following a set of rules to do Lewis structures. So, yes, by going step by step by step, in step 7, yes, we take it from oxygen and give it to silicon. But in the real world, what we're trying to explain here is that we incorrectly assign those electrons to oxygen in the first place. They were never supposed to be with oxygen. But again, because we're following a set of rules like a cookbook, then we have to go back and fix what turned out to be a mistake by putting them there in the first place. I hope that makes sense. We're not really doing crazy things here, is the message I want to get across. All right, the final thing. What's central atoms, what can they do? What are they allowed to do? Well, first of all, I talked about this before. Hydrogen cannot be in the middle. Helium can either, but helium never bonds, ever. So hydrogen cannot be in the middle, ever. Only terminal. Then we have 5 elements in the second bullet. Hydrogen, helium, lithium, beryllium, and boron. Those elements can have less than an octet. They can have 2 bonds in the case of beryllium and lithium. They can have 1 bond in the case of hydrogen and helium, or they can get away with 3 bonds in the case of boron, which we do see quite a bit in chemistry. Beryllium and lithium, they're 2 bonds. We do see it some, but they do ionic bonding a bit too. And then because helium doesn't bond at all, we can pretty much ignore it. So we have just a few elements that can have less than an octet. Now, this is somewhat surprising for students every year. There are only 5 elements: carbon, nitrogen, oxygen, fluorine, and neon. And we're going to ignore neon because it doesn't form compounds either. So we have practically 4 elements that will only ever have an octet. Those 4 elements must always have 4 pairs. It could be 4 shared pairs. It could be 3 with a double bond. Whatever. Total, there will always be 8 electrons around those atoms. No exceptions to that whatsoever. Which then means that almost every other element, especially the nonmetals, beginning on row 3, can have an expanded octet. So most elements on the periodic table will be able to expand the octet. Why? Well, it goes back to our understanding of the Bohr model and the quantum mechanical model. On row 3 of the periodic table, those elements represent atoms where the electrons have begun to fill up n equals 3. And on n equals 3, those atoms have d orbitals. And because the d orbitals don't get filled until a little later, they are empty and available for extra electrons to be squeezed into them when you need to expand an octet of something like sulfur or something like phosphorus or chlorine. The P's are full, but if I want to squeeze more in there and expand it, it'll go into a dxy or a dyz. All right, so that's a very important topic with Lewis structures. We're going to draw 1,000,000 of these, so don't get behind on it. If you have any questions, come by and we'll practice until you got it.